Okay, hello everybody to our edition of Quasiworld today. So our first speaker is AdiGlücksam, and she will tell us about the multifractal spectrum of planar harmonic measures. So please, Adi.
Thank you. Thank you for the opportunity to speak here today. As Mario said, I'll talk about a joint work with Ilya Binder, discussing multifractal spectrum of planar harmonic measures. Let me start with describing the setup. So the setup for today's talk, we have a simply connected domain in the plane. And for brevity, I'm going to oftentimes write for this just SC. And we know that whenever you have a simply connected domain by the Riemann mapping theorem, we have a Riemann map from the disk to omega. So a good picture to keep in mind is something like this. I'm going to call it the anglerfish. So on one hand, we have this map, and on the other hand, we can associate a harmonic measure to it. And I don't know if it's lucky for us or not so lucky for us, but there are several ways to view harmonic measures. Let me just recall, at least in terms of feeling, because we're going to use that for some of our arguments. So if you come from the world of probability, the harmonic measure will be the probability that a random walk starting from your initial point, Z0, exits the domain through some arc A. If you come from the world of PDE, you might say that, well, harmonic measures are used to solve the Laplace equation with some initial conditions or continuous. But the definition that I want to use today is actually as the pullback measure or the push forward measure, depends on how you look at it. So we're going to look at the normalized length of the disk, and we're going to measure the pre-image of my arc. So this is a definition that will play a key role today. Put it here so we won't forget. And well, if you worked with Riemann mappings, you might tell me, well, you know, it's not always the case that this map is even defined on the boundary. So how can you use this as a definition? But there are theorems showing that, you know, if you exclude a very, very small set, capacity zero set, what's called, then we're okay, and we can use this definition. Now, if once again we investigate this relation, we see that there should be some connection between the decay of the harmonic measure near some point and the derivative of this phi. And it's this connection that we're going to discuss today. So without further ado, let me present some definitions. Minkowski spectra. So the first definition I'll present comes from the conformal realm, the realm where you have this Riemann mapping theorem. It is called the Minkowski distortion spectrum. And the role of this is indeed to measure some kind of distortion. So the definitions I will say now are not very precise, and you should take them with a grain of salt. but they do convey the idea and where the problems are and all those things. And so let me write that these are definitions, not full accurate definitions. So this is going to be the dimension of the set of points on the boundary of the disk where the derivative, to take a step back a little bit, is going to behave roughly like 1 over 1 minus r to the a. So you can see that we have here a parameter a. This is a function which depends on the domain, and this parameter a. And a is going to be a real number for now. You should think of r as growing to 1. So what do we do here? We fix a direction on the unit disk, on the boundary, and then we look at the line connecting the origin with this angle, and we look at how the derivative behaves along this line as we grow near and near the boundary. Okay, the second guy, this one should come from the potential realm, from harmonic measures. Call it the Minkowski dimension spectrum. This will once again will be a function which depends on the domain, except some subset of the real line. And as before, we're going to measure the dimension, but now instead of looking at points on the boundary of the disk, we will look at points on the boundary of the domain. And instead of looking at the way the derivative grows, we'll look at the decay of the harmonic measure. So the harmonic measure of a disk centered at xi with radius delta should decay roughly like delta to the alpha, where alpha is my parameter. Okay, and as I said before, we will be looking for some relation between these two quantities, or in other words, some relation between these two quantities will give me exactly what I discussed earlier, that somehow the decay of the harmonic measure and the derivative of my Riemann map should be related. And I guess the first question to ask is, why would this be interesting? Well, let me talk a little bit about motivation. And I will only present 3 pieces for motivation here today, but there are many, many more. So the first one is Brennan's conjecture. First of all, what is the conjecture? You look at the following integral. So pick some domain omega, and we start over. So we start with a simply connected domain. And we let little phi be the Riemann map from omega to the disk. So if you try to compare this setup with our setup, you see that little phi is the inverse of our capital phi. And the question is, for which p's does the integral of the derivative to the power p converges? But you want it to be for all domains. Some kind of a universal question. So what do we know about this? So this is a question from 78, basically. It was first appeared in a paper by Brennan, as far as I know. But a lot about it was known from a little earlier, but not much. So Brennan mentions in his paper that it is a fairly recent question. At the time, it was known that if P is between 4/3 and 3, we have convergence. And Brennan showed in his paper from 78 that if P is equal to 4, and if P is equal to 4/3, then it diverges. But then you can see that there's still a gap. And the gap is 3 versus 4. And since then, a lot of people have been working on these. Some advancement has been made. As far as I know, the best P that we have today for an upper bound is 3, still less than 3.5. So not very great. And you may ask, well, what is the connection between Brennan's conjecture and these spectra? So let me tell you about the connection. The connection is through an object called the integral mean spectrum. This is just, well, there's a different definition for it, but right now I want to describe it as the Legendre transform of the Minkowski distortion spectrum. You take supremum over all A's, and you look at the linear combination d omega of A plus A times T. And Brennan's conjecture holds if and only if, when you look at the universal integral mean spectrum. So you take supremum over all simply connected domains, and you evaluate the integral mean spectrum at -2, then you get 1. So in a sense, knowing something about the distortion spectrum will give us information about the integral mean spectrum, which in terms might help us solve the Brennan's conjecture. Another connection between the integral mean spectrum and the project I'm describing today is a paper by Jones and Makarov from 95, which I will repeatedly mention. They showed that if you look at the universal integral mean spectrum evaluated at 2 minus epsilon, this is equal to 1 minus epsilon plus an error term of epsilon squared. So of course we should think of epsilon as going to 0. Okay, so this is one motivation. The second motivation that I would like to briefly mention is Littlewood's constant. Where the question asked was, you're given a polynomial of degree n, and you're asking for which, or what is the optimum, which alpha. If you look at the hyperbolic derivative of g, it will be bounded by n to the alpha. So again, this is a question which is posed in the world of maps. It looks like it has no connection with harmonic measures, but Lewis and Wu, they were building upon an initial idea of Yermenko and Sodin, used a similar connection to show that you can choose alpha to be less than 1/2 minus 2 to the minus 264. And they again use the extremal behavior of harmonic measures. These are two examples where you have a question on some entire map, formal maps and polynomial, and you can get a lot of information from relating this with the harmonic measures. And so the third example I want to bring is actually an example where the reverse holds. And that's Makarov's dimension theorem. It was done in 85. And the result is quite ingenious and simple. If you look at the dimension of the harmonic measure, it's always going to be equal to 1. And what's really cool about this result is that he used the connection between, in a sense, he used this connection, but what he did was he used the fact that log of phi prime is a Bloch function, and Bloch functions, in a sense, behave a little bit like martingales. And so you can copy proofs done for martingales for these Bloch functions. And so he used actually properties of phi in order to say something about the harmonic measure, because the reverse connection. Okay, so I hope that by now, at least I convince you that this is an interesting connection to investigate. But what exactly is this relation that I keep mentioning? Or why would it be true? So our story begins with an argument originally done by Alfors in the 30s. And his idea is based on the mean value theorem. Well, what does the mean value theorem tell us? It tells us that the quotient between the difference between the images and the difference between the distance between the points, this is equal to the derivative at some point, which is going to depend on x and y. Now let's try to analyze this equality. Move it a little bit. So this is just the mean value theorem. And let's try to take some disk. They are x and y, are these x and y in the pink area. You know what, I apologize. Let me take a different point. So let's take this disk here. Okay, so I have this disk, and I look at the preimage of this disk, and the preimage, say, sits here somewhere. So I'm going to have here, say, 2 points, say A and B, and they somehow correspond to these 2 points, A and B. Now, what is the distance between phi A and phi B? The distance between phi A and phi B is the length of this chord, which is comparable with the diameter of the disk. So this top part here is comparable with the diameter of the disk I started with. Okay, what about the distance between A and B on the boundary of the disk? Well, this is essentially the harmonic measure based on this definition, right? We look at the curve inside the disk, it's this curve. The preimage of that curve is exactly what's connecting A and B. And so the numerator is comparable with the harmonic measure of the disk. And so you see here how there's a connection between the harmonic measure, the decay of the harmonic measure, and how fast the derivative grows. Now, you might stop me and say, wait, hold on a minute. You just said that the Riemann mapping theorem might not even be defined all the way to the boundary, which is true. Yet there's a theorem by Kobe's distortion theorem. From 1907 that tells us that roughly this is okay. So what does it mean? It means that if there exists some arc on the boundary of the disk satisfying 3 conditions. So we want the image of the arc to sit inside my disk. B, we want the diameter of the disk to be comparable with the diameter of the image of that arc. And we also want that the harmonic measure of the disk will be captured by the length of the arc. If those 3 conditions hold, then this connection between the derivative at a point and the decay of the harmonic measure will be correct. Now, of course, the person who used this in the connection of the Minkowski distortion spectrum and the Minkowski dimension spectrum is Makarov in his work in '98, where he coined these expressions. However, there's a small crack in this beautiful connection, and that's exactly this pink if. Let me take a break here and move to the next board so we can talk about this if. Also steal these 3 requirements that we need. Okay. Great. So our problem is with the word if, and let me take you now to a different disk. So beforehand, to explain the argument, I was looking at this disk here, right, with this preimage, and I would like to look at a different disk. I would like to look at this disk. And my disk abilities are not right this morning, I'm sorry. Okay, so in order for us to see anything, let me enlarge the picture. What exactly do we see here? So there's the disk, and then there's a purple arc, which is very, very, very big. And there's a pink arc, which is very small. Now, I'm looking to find one arc on the boundary of the disk that satisfies these 3 conditions. So in order to satisfy the first condition, there's no point in looking outside my disk. Okay, so I have these 2 conditions about capturing enough harmonic measure and having large enough diameter. And I have 2 options, 2 choices. I have the long purple arc. Well, that long purple arc indeed has diameter comparable with the diameter of the disk. But if we look at the harmonic measure, well, let me take you back to the first definition I presented that comes from probability. Well, the harmonic measure of this arc is the probability that a random walk starting from this Z0 will hit this arc. Well, a random walk starting from this Z0 has to travel through this very, very narrow pipe. So the probability that it will hit this purple arc is very, very small. So in a sense, this arc has good diameter, but small harmonic measure. And if I will try to extend this arc to capture enough harmonic measure, it will just be way too big, okay, because I have to take most of the tunnel. On the other hand, if I take my other choice, so my other choice is the pink arc. Well, the pink arc, on one hand, well, because it sits outside here in the beginning of the mouth, well, the harmonic measure is basically linear, right? Because a random walk from Z0 here is pretty easy to reach. And so it's going to have good harmonic measure. But the diameter is too small. And if I increase the diameter, well, my harmonic measure is going to explode. So in a sense, if I choose this arc, the purple arc, then I'm counting this disk in the wrong alpha, because the alpha should be much, much bigger. And on the other hand, if I try to choose the pink arc, well, I'm counting it in the wrong scale. And so for many years, it was believed that, you know, it's okay, but it's probably an ad hoc kind of phenomenon, or something that only happens until, you know, some finite number of scales, and probably will not propagate into a serious problem. However, we discovered that indeed it does propagate. Into a problem. So let me show you what the problem looks like. Let me take this. Oops. Okay, so this is our first counterexample. We call it the feisty Pac-Man. And you can see that the same problem, well, we have these teeth, and every teeth corresponds to such a problem, because in every teeth, we're going to take a disk, like so. And when you enlarge it, then you see, well, as before, I have two choices of arcs. One arc will have large enough diameter, but not enough harmonic measure because you have to travel inside. And the other arc will be too short. It will carry most of the harmonic measure. Now, what does this contradict? I forgot to mention. The argument that I explained earlier translates into the following inequality. So once you plug in, remember that you have to take your R corresponding to a specific delta, and so the inequality that we expect between these two quantities is the following inequality. So this is what we expect to find. Let me call it the Anglerfish inequality. However, this feisty Pacman shows you that this is not always the case. And in fact, you might look at this argument and you might say, well, the problem is in the fact that you have too many arcs in the disk. Maybe if instead of disks, you're going to count curves, maybe that will solve the problem. So for this, we have a second counterexample. That works with slits. You don't have to use slits, but if you use slits, it's easy to see why counting curves instead of disks will not solve your problem. And let me make some space. As before, the idea is this. So you have these dashed lines are slits, and you can see that they're nested. So for points here in the intersection of all these slits, this is where we're creating the problem infinitely often. And looking at this picture here, you can see what the problem is. So if you fix one specific scale, which is say this scale, and you take a disk somewhere near these points, once again, you have two options. You can either choose the inner curve, the blue curve, but it will cost a lot to get in there, and so the harmonic measure is very small. Or you can choose the outer one, which has a lot of harmonic measure, but it's too small. So this brings us to our first theorem. Construction with the slits can be done on a set which is as close to 1 as you want. So for every alpha bigger than 1, there exists some domain omega such that, well, basically anglerfish fails. Okay, well, this is a bit of a bummer because I gave you motivation. I said there are all these nice results, and they use this connection. Many of them use something which is called, it's a reduction to self-similar sets. And now it's no longer clear whether these still hold or not. However, if you look at these three conditions do hold for a vast collection of examples, which are quasi-disks. So theorem 2 tells us that if omega is a quasi-disk, then the anglerfish holds. Okay, well, here's the problem. All of the problems, all the nice connections in the motivation that I showed you, they all looked at some universal bound. Even here, you see I wrote I, the integral mean spectrum. This I is defined by taking supremum over all simply connected domains. And all the questions, if we look for a second backwards, you see that all the questions have this thing that repeats itself, all omegas, or G was a general polynomial, or here we looked at all harmonic measures. So for the most part, this connection is used with some universal bound. And so perhaps even though theorem 1 tells us it's not correct for all domains, maybe using the fact that theorem 2 shows that there's a vast collection of examples where it does hold can somehow save the universal guide. Okay. Well, specifically this idea of using a universal guide, I want to look at specific subclass of these subdomains. Before that, let me define the universal guides. So universal bounds. So the universal spectra, these are the ones that are used in these problems where you want to know something about all the domains. And so they're defined to be, so the universal Minkowski dimension spectrum. This will be the supremum over all simply connected domains, so little f. And the universal dimension spectrum, sorry, distortion spectrum, going to be again supremum over all simply connected domains of d omega of A. Now, instead of looking at general quasi-disks, I want to look at a specific subclass which relates to symbolic dynamics. And to start this discussion, I would like to take us back to our very much favorite Koch snowflake. So how do we construct the Koch snowflake? Oh, we start with just a line. We replace the middle third by an equilateral triangle, and then we repeat this process. We replace every arc with a copy of that polygonal line over and over again. Now we can associate the Koch snowflake with linear maps, specifically 6 linear maps. Well, you might look at this and say, well, why 6? You can just, take each one of these little guys and copy it here. But there's a problem. You see, my maps, they need to be defined in a small neighborhood of my arc. And so if you look at this part here, for example, you see that on the left side, it has a small angle, pi over 3. But on the right-hand side, it has a 4 pi over 3 angle. So I cannot map it to this guy, which has 2 small ones. But if you go one layer down, then we're already okay. Okay, because we can map small angle, large angle to small angle, large angle, and small, small to small, small, and everything's okay. Now, if I associate every map, so every map gets some kind of a letter. Every map corresponds to some A in some alphabet. Then almost every point in my snowflake has an infinite word that describes it. And if you apply the shift to the word, you erase the very first digit. This corresponds to applying phi of, say, W1 to my point. So we have this nice connection. And now the first person to connect this with potential theory was Carlson in 85. He looked at it and he said, okay, why triangles? Why not replace the triangle with a general polygon? There are some issues with it. For example, you have to make sure that after many iterations, somehow your curve is not self-intersecting, and this is one of the most difficult, still open problems. However, this structure, this connection with symbolic dynamics that I described here, where a point corresponds to an infinite word and the shift corresponds to applying the map, this additional structure allowed him to get a lot of information about the harmonic measure. In particular, he has something which is called Carlson estimate. Which basically tells you that if you look at the harmonic measure of two arcs described, an arc described by a concatenation of two finite words. So what do I mean by that? Well, a finite word gives me a recipe of which maps to apply. So for example, from here to here, I'm going to choose, say, I'm starting by choosing this arc, so now I'm here, and then the second digit tells me, well, choose this arc, so now I'm here, and then the third digit will tell me, well, choose this arc, and so on. So every word gives me a recipe or a path, an instruction of how to get to my arc. And he showed that the harmonic measure of the concatenation of two words is the same as the product of these two harmonic measures, where the constant depends on the domain. This a bit here. So the constant here depends on the domain. Let me write it in pink. This depends on the domain. But now you can see how using these type of symbolic dynamic objects can help us with this approximation problem that I described earlier. We want to know something about inequality anglerfish for the universal guys. Well, we know it's not always true because of theorem 1. Theorem 2 tells us it's okay for quasidisks. So I want to approximate it with quasidisks. But a general quasidisk, well, wouldn't be much good, because if I approximate a specific scale, nobody promises anything about future scales. However, Carlson's estimate does help us. Why? Well, I'm going to take a picture at a specific time. I'm going to approximate my domain with a polygon at that specific time, and then I'll create some kind of Carlson domain out of it. And this property, this Carlson estimate, will guarantee that the end product is going to replicate the same spectrum. So this brings us to theorem 3. Which has 3 parts. First one tells us that you can approximate the universal spectra by looking at repellers. Repellers are some kind of generalization of Carlson domains, but you can keep this idea of Carlson domain in your heads. The second part tells us that we can approximate also the distortion spectrum using this. And then the third one uses some special property of these repellers, and that tells me that anglerfish not only holds for the universal guys, but we actually have equality. Now, before I dive into the idea of the construction, let me say something about the history of these results. So some history and credit. So theorem 2, without the requirement of quasi-disk, was initially proved by Makarov in 98 in his paper, and has later been extended by Binder in 2008. However, both had the crack that theorem 1 describes. Theorem 3, so part 2 was proven initially by Carlson and Jones.
So Adi, sorry to interrupt. So what is theorem 2 again?
Yes. So theorem 2 tells me that there's an inequality for quasi-disks. So if you don't have an inward cusp or outside cusp, then you're good. In fact, the conditions that we use, sorry.
But what do you mean without quasi-disk? I mean, so they had a stronger result, but they don't need the quasi-disk assumption?
They overlooked the problem that we found in theorem 1.
So meaning what?
There seemed to be a crack in their proof.
Oh, I see.
And actually, this might be interesting for you. The reason why we need the quasi-disk is because, well, if the harmonic measure is doubling, then this problem of diameter versus capturing enough harmonic measure disappears. And the second thing we wanted is you wanted the distance between, well, basically two arcs, right, is comparable from the inside and outside. So these are the two things that we use quasi-disks for. Right, so history of theorem 3. So Carlson and Jones showed part 2 in 92, and then later Makarov showed something similar also in his paper from 98, and Binder showed again something similar in 2008, but they all only focused on part 2. And the reason was, well, if you think this inequality is always true, then there's no reason to approximate the dimension spectrum, which is much harder to work with. And so we were the first to actually show one, and also we tried to write as many details as we could. Well, in the 5-7 minutes that I have left, I think I'd like to say something about the construction. One more thing that we did, because we wanted to work with these symbolic dynamics, one of the things that we created is kind of a dictionary between the different definitions. So, for example, we have a definition of dimension spectrum and Minkowski spectrum in terms of words, and we show that it's the same. You get the same thing, but instead of counting points on the boundary, you can count words, specific sequences of words. And we had to have a refinement of Carlson's estimate. So let's start with what is the plan of my construction. Perhaps I won't have time to say more than just what is the plan of the construction. So the plan of the construction is not the most fascinating thing, but maybe I'll have time to point out the difficulties. So you start with finding a domain such that the spectrum, whose spectrum is close to the universal guide. So notice that I have a parameter, A or alpha, and the domain that is close to the universal guy might change with the parameter. So I fix a parameter, and then I find the domain. And then after that, I have to fix a scale such that counting, say, how many disks with diameter delta and harmonic measure delta to the alpha captures enough of, say, the universal guy up to some error. Okay, so I fix the scale, and now I take a picture of that scale and I approximate it by a polygon. Now, as I mentioned earlier, when you approximate a specific scale, nobody promises that the behavior that you get in that scale is going to propagate into smaller scales. However, if you use Carlson estimate, it guarantees that the spectra is preserved. So this is not really a new idea. The place where we contribute, the new things that we do, is, first of all, the step of how to approximate. So we start with some domain. So we start with some domain, and the first thing that you have to do is you have to identify the important parts of the boundary. So for example, in this domain, all this bit here is not very interesting, but these guys are going to be interesting. They're going to have harmonic measure which isn't linear. So, oops. Well, we're missing a guy here. We found these things. Later on, I'm going to symmetrize my domain, but for now, let's just look at the upper half. The second step after doing that is to cover the rest of the boundary with disks. And how small these disks will be, these pink ones, that is going to depend both on delta and on alpha, because you want these disks to not disturb the harmonic measure at all. They're going to be very, very tiny, just to have a polygonal curve. And then in the next step, what I'm going to do is I'm going to replace my curve with a polygonal curve. That's the orange bit. Let me sorry about that. Let me show you what it's going to look like. So this is the domain is going to look like this. I'm missing one line. And if you try to compare the two, then I have a figure of comparing the two. There it is. So you see here we're comparing the two figures. And you can see that near the place where there were very, very small disks, there's barely any difference. But here near the large disks, well, the difference is like delta to the alpha over 100. But the problem is it accumulates. And so the first difficulty was to show that while the changes in these large disks are very small, they're accumulative, but we still only lose about half of the disks in the initial set. And when we did that, we used an argument which is reminiscent of Jones-McCarver from 95. So they have this key lemma, and the argument is not based exactly on the lemma, but if you read it, you see that it kind of reeks of the same ideas, which is nice. And then we cover again, and we just create a repeller. So the first struggle was this argument that we don't lose too many disks, and it was a struggle because it takes about half of the entire proof. The second problem is something that I mentioned earlier. Carlson estimate, the constant depends on omega. And because we start from a specific scale, this constant can mess up the harmonic measure pretty badly if you don't know anything about it. However, we show that if you choose your maps to have some certain some kind of extra property, then you can control this constant and have that this constant is like, I don't know, 100 or something fixed. Well, I can stop now, or I can say a little bit about future plans. That depends on time. Mario, do you want to?
Well, so maybe you can stop here and we can start the discussion. Yeah, and then maybe you can make
sure.
comments. Okay, yeah. So
Thank you.
Let's thank Adi. Yeah, and are there any questions or comments? Well, maybe you can say something about future directions, Adi.
So let me just remove down here. Right. So the future direction that we still want to do the first one comes from the following observation. The absolute value of the derivative is exactly the exponent of the real part of, say, some branch of the logarithm of the derivative. And so it makes sense to ask, well, what about doing the same thing for the imaginary part? Well, we know that the imaginary part, this is basically the argument again. Once you choose a branch, and just like the absolute value of the derivative corresponds to the decay of the harmonic measure, apparently the argument corresponds to something which is called the rotation, which is basically how much the boundary coils around a point. And so you have an extension of both spectra to also take into account the argument of the derivative or the rotation. And then the first thing we want to do is to extend these theorems for this generalized thing. So for theorem 2, actually, this is already written. This is already extended with rotation. What we still have to do is theorem 3. So we need to somehow make sure that we also approximate the rotation. We believe it should be okay and straightforward, but still needs to be written. The second thing that we want to do is, well, sometimes inequality anglerfish is used for specific sets. And so we want to investigate these specific sets and see whether it holds or not. Specifically, there's the problem of Fraunhofer evolution where this is used. So these are family of random planar curves that are conjectured or proven in some cases to describe the scaling limit of an invariant stochastic processes in the plane. And this is used a lot. For the experts, we are suspicious about kappa equals to 4. And that's all I'll say about it now. Third thing is to reduce the number of maps. So currently, the maps that we use, you have a map per every disk, and there are a lot of disks. We want to globally bound this and see if it can be done with, I don't know, 10 maps or something. Using some approximations. Another very interesting collection of questions to ask is about computability of these objects. So we have a joint project with Cristobal Rojas and Michael Yampolsky showing that for simply connected domain, the harmonic measure is what's called uniformly computable if and only if the boundary is computable. And so it would be interesting to know, is it possible that, for example, the harmonic measure is computable, but the spectrum isn't? the spectrum is computable, but the harmonic measure isn't. One spectrum is computable and the other isn't. Anything about universal guy? There's like a long list of questions that you can ask there. And the last thing that we want to do is to generate some concrete examples with lower bound. So this has been done by Belayev and Smirnov. In I think it was 2010, but they only generated random examples. So they show that such an example should exist almost surely, but there's no concrete example to look at. We're hoping to be able to generate something concrete. That's it. Thank you.
Yeah, thank you. I have a quick question. Is there any chance that some of your examples somehow can arise from complex dynamics? I think there was some kind of relation like this by maybe.
You mean these examples?
Well, I mean, if I understand you right, your examples come from some kind of a self-similar construction at the end of it. Right? Is that right?
Yes. Well, okay, first of all, the examples, that ruin the inequality, they are self-similar and also not self-similar. So they're self-similar in the sense that you see the same picture over and over again, but the scales, the ratio between different scales is not bounded. Because if it were bounded, then you would have, right, a quasi-disk. Yeah, it is surprisingly how much we don't know about this. So I would expect that if you have like a snowflake, then surely we know the spectrum or stuff like that. But no, it's not clear. I'm hoping that maybe with this Carlsonian estimate, the refinement of Carlsonian estimate, maybe we can do something, but we don't know.
Are there other comments?
The struggle with
sorry.
The struggle with complex dynamics is just that you're using only one map, and so
yeah, but you might think of some kind of, I don't know, quasi-conformal gluing techniques, right? And then you apply, I don't know, the measurable Riemann mapping theorem to make things. I mean, I'm just speculating here.